Welcome back. Our previous video introduced identification for the factor model, and in particular, that we needed to make some additional normalizations on variances or factor loadings in order to be able to get identification of the model, and also that we might need to make additional normalizations to be able to interpret the model properly. And in this video, we'll tackle the important question of how do we actually obtain parameter estimates for a factor model given a set of data. And as you'll see, estimation can be quite challenging in this setting, and all sorts of algorithms have been concocted to try to make that easier. And this will connect pretty closely to what we talked about with mixed logit and preference heterogeneity in a prior video. We'll start with a general approach to estimation and then walk through a very specific example that relates to the measurement error and proxy variables video in this series. The question of how to estimate factor models is basically that we impose distributions on theta and epsilon, and then once we assume that they're, for example, both multivariate normal but independent of each other, then we can just estimate the parameters by maximum likelihood. So we can get the coefficients on the covariates in the measurement system, which is beta from a prior video, the factor loadings, the variance covariance matrix of the factors, if we haven't normalized it to identity, and the idiosyncratic variances of the loadings. And because we don't observe theta, we're going to have to integrate it out of the likelihood function. And that's where things can get a little bit tricky or gnarly or whatever unpleasant word you have. And to do this, we either need to do quadrature or Monte Carlo integration. We could do simulated method of moments. We could do Bayesian Markov chain Monte Carlo. We could use the EM algorithm or the MM algorithm. And as you may be aware, these all vary in their ease of use and how you want to tailor them to the problem at hand. Why do we use factor models? Well, it's because we want to get around the omitted variable bias problem without introducing measurement error. So let's think back to the log wage regression from earlier in this series, where we were thinking about proxy variables for cognitive ability. So if we omit cognitive ability from the regression, then we're going to get a biased estimate of the returns to schooling. This is classic omitted variable bias, but we'll also get attenuation bias if we include some proxy for cognitive ability like the IQ score. And let's just suppose that we have measurements of cognitive ability, multiple measurements, and we know that they're correlated, but that they're each measured with error. So then what we do is we can just estimate the parameters of this model by maximum likelihood. And in particular, we have a system of equations that we can obtain the likelihood of each component, multiply them together, and use that as our overall likelihood. And I'll show you that momentarily. And depending on things, I may make a video doing a coding walkthrough of this at some point in the future, but not in the near future. So let's go through this system of equations a little bit more. So let's pretend that these measurements of ability are ASVAB scores, this ASVAB. It's something that the U.S. Armed Services military uses to assess the skills of its soldiers. So this is called the Armed Services Vocational Aptitude Battery. It's what ASVAB stands for. And there's a bunch of different subtests, maybe one that tests your verbal, one that tests your math, one that tests how good you work with your hands in terms of understanding spatial reasoning and such. So there's a lot of tests in this battery, and we can just take the score on each of these subtests that has to do with cognitive skills, and that's what each of these ASVAB J is going to be. So maybe I have a dozen of these, maybe I have half a dozen of these, and I'm including the same covariates in each one, but the loading, so the coefficient on that covariate is going to be different, and then also the factor loading on this random factor psi is going to be different. And then, of course, there's the uniquenesses as well. So I have those system of equations, and then I have a log wage equation that's just my normal log wage equation, but I'm recognizing that it's also a function of this latent cognitive ability. And I assume that this cognitive ability is standard normal distributed. So again, I've pinned down 1. I've normalized the variance to 1. as instructed in the identification video. If I didn't want to do that, then I would have to normalize one of these alpha j's to be 1. So those are our system of equations. So we have capital J plus 1 equations. And then we just write down the likelihood. So we assume that the epsilons and the eta are all normally distributed with some unknown variance, and each of the epsilons has a different variance. And then once I do that, I can write down the likelihood function like so. So what is the phi here? Well, the phi is the standard normal PDF. So that's why I'm dividing by sigma and then also multiplying by 1 over sigma outside of it. And then because I have j of these ASVAB scores for each individual, I'm going to take the product of all of these, and then I'm also going to take that product and multiply it with the log wage likelihood contribution. So this is pretty standard for like estimating a regression model via maximum likelihood. We have basically capital J plus 1 regression models that we want to combine together. And so this is our likelihood function, and then we can just take the log of that, take the sum of those log likelihood contributions. That's our overall log likelihood. And then the only trick is that I have an integral inside the log because I have to integrate out this psi because it's unobservable. So hopefully you're getting shades of mixed logit when you see this likelihood equation at the bottom. But that's basically how we would do this for the straightforward example of I want to estimate returns to schooling. So years of schooling would be an X. And then I know that there's this other random factor that is unobservable that is capturing cognitive ability. And so I want to include that in the model as well. And then some people don't like that this psi is uncorrelated with X. So it's basically a random effect instead of a fixed effect. But there's ways to get around that, as we'll cover in the next slide. And that brings us to dynamic selection, which is also a concept we talked about previously when thinking about preference heterogeneity. So the idea with the returns to schooling is that people with higher levels of cognitive ability will select into schooling, and then that will give them higher wages. And what we don't know is, are the wages higher because they went to school, or is it because they had a better endowment of cognitive ability? And so the way that we can do this is we can actually model the selection into schooling as well as the payoff in terms of the wage effect of having more schooling and more cognitive ability. And so we would just add another layer of equations to the one that I had on the previous slide and then estimate that likelihood function. So the ability factor is like a preference heterogeneity for how do I like schooling. So people with higher levels of ability will presumably find schooling easier, and so they're more likely to go to school. And that's going to induce a correlation between schooling and wages. So it is an omitted variable bias argument that we're making, not a simultaneity bias or measurement error argument. And then the assumption that we're going to make, which we talked about in the prior video on dynamic selection, is that we're going to assume that conditioning on this factor will eliminate any other endogeneity so that the likelihoods can be separable. And then once we do that, we can just add the likelihood for the choice, the schooling choice, into this equation. And then we have a similar likelihood that we had before. And what I wanted to get at with regards to the dynamic selection is that we don't necessarily have to assume that schooling and cognitive ability are independent anymore. We just have to assume that they're independent in the initial period of the model. And so if we have a dynamic model, we can say, okay, well, at the initial stage, we have this random factor that's uncorrelated, but over time, that random factor will become correlated with schooling through the choice equations that we're modeling. So that is something to think about in terms of how dynamic selection works. And hopefully it provides a little more intuition for you as to what dynamic selection is, because we're basically saying that we start out with some endowment, and then we're making choices conditional on that endowment, and then that's going to induce a correlation as we go further in time. So hopefully this kind of brings you back to the mixed logit and preference heterogeneity unit that we covered earlier, and that this stuff is kind of coming together nicely for you. So the thing to kind of think about in how is it different than preference heterogeneity? Well, we're going to have a random factor, not a random coefficient. So that's the main difference. So with the mixed logit model, we had a random coefficient on something like price. But here we're having an unobservable characteristic about the product, and then there's still systematic responses to it. So it's a little bit different, but it's closely related. So that is how we estimate factor models. And then in the remaining 2 videos in this mini series, I wanted to walk through some foundational papers that established this method of estimating factor models, and also what's at the frontier these days in terms of econometrics and applied econometric papers that are using these models. So I hope you'll find the next 2 videos beneficial, and I hope to see you there.